important definition to understand for what we're doing moving forward is something called a reference angle. Okay? And we're going to have to make sure that we add it's the acute, and you can add the word positive there. Acute means between 0 degrees and 90 degrees. So a reference angle for all 4 quadrants is the acute angle, or the angle between 0 and 90 degrees, that the terminal arm makes with the nearest x-axis. So I'm going to highlight that in blue in each of these. There's the nearest x-axis, there's the nearest x-axis. It doesn't matter which way I put the arrow. I kind of like the arrow when I did it this way. If we go back to the nearest x-axis, what angle is that? So in this example, they took 35 degrees and they made that the same reference angle for each of those. So we would say that an angle of 145 degrees has a reference angle of 35 degrees. Does it make sense to you that you can figure these out? Because I'm going to give you 145 degrees and I'm going to say, what would be the reference angle? And so we use a little bit of a logic here. That halfway around, does halfway around make sense that that's 180 degrees? And so if I want to figure out what's left, if I had 145, I could take 180 minus the 145 and then I'd find out what my reference angle would be. In this one, if I gave you 215 degrees, and I wanted to figure out this part, well, I know halfway is 180. Can you see that you could take 215 degrees and minus 180 degrees, and that would leave you with what's left. So it's a little different in each quadrant depending on what you're thinking about. In the last one here, if I wanted to find the reference angle, I would take 360 degrees, because that's all the way around, and I would subtract the 325 degrees. And that would give me my 35 degrees. All right, I'm going to move this over here. Now, why do reference angles matter so much? And how does it help us with angles above 90 degrees? First of all, we go back to our original understanding of sine, cosine, tangent, right? I could, here in quadrant 1, pick any point, go straight down, and make a right angle triangle. And I could measure the opposite side, I could measure the hypotenuse, I could measure the adjacent. And my calculator has all of those ratios built in. So right now, this is quadrant 1. We're going to figure out these from our calculator. So I'm going to turn my calculator on. I'm going to look at what sine of 35 degrees is, cos of 35 degrees, and tan of 35 degrees. And I'm going to write those values down. So 0.574 to 3 decimal places, 0.819, and 0.700. Interesting. Even though it rounds with zeros there to 3 decimal places, we would write all of those zeros. Okay? Now, in quadrant 2, I could take any dot on the terminal arm and I could go straight down to my nearest x-axis. In fact, if I picked that dot so that the hypotenuse was exactly the same, it kind of looks like I almost made it exactly the same as the first one, would you agree this is exactly the same triangle as the one in quadrant 1? And if I did opposite over hypotenuse in this triangle in quadrant 2, it should be exactly the same as the opposite over hypotenuse of the same triangle in quadrant 1. I've just flipped it over. But some things a little bit interesting happen. So watch what happens. I'm going to go quadrant 2 here. I'm going to go to my calculator and I'm going to do sine now of 145 degrees, cos of 145 degrees, and tan of 145 degrees. And I start off with sine of 145 and I push enter and I'm like, oh, it is exactly the same. So maybe this is how we do trig. We just keep everything the same. But then when I tried cos of 145, I'm like, oh, it's the same, but this time with cos it's negative. That's kind of interesting. And if I do tan of 145, oh, it's negative as well. That's interesting. So I go and I write things down and I'm like, this is still 0.574. This one was now negative 0.819. And this one is now negative 0.70. Quadrant 2. Now if I pick the dot on my hypotenuse and went back to my nearest x-axis here, that would be the exact same triangle again. And this time, I'm like, okay, predictions in quadrant 3? Well, if it's the exact same triangle, I'm going to guess that sine of 215, cos of 215, and tan of 215 I'm going to guess that they're going to be exactly the same, but I'm a little bit curious about the negatives and the positives. All right, so guesses. So my guess, sine of 215 will also be 0.57. Do you think the sign always stays positive? Maybe that's the trick. New seating plan, you are behind Danny over there, where the jacket is. So maybe sine is always positive. Let's check it. Oh no, sine is negative. Well, maybe cos will be positive then. Oh no, cos is still negative. Well, maybe tan will be positive. Or maybe they're all negative. I don't know. Well, actually, I do know. But, oh my goodness. So now, this is interesting. The numbers were the same. Wow. But this time, the sine was negative. The cos was negative. But the tan was positive. And we have one more quadrant to go. Quadrant 4. sine of 325 degrees, cos of 325 degrees, and tan of 325 degrees. Any predictions? First of all, does it make sense that if I made a dot on here and I drew it back, it would make the same triangle? And it actually doesn't matter. Remember trig, the power of trig? If you have an angle, it doesn't matter how big or how small that triangle is, the ratios, like sine is opposite over hypotenuse, that ratio stays the same no matter how big or how small that triangle is. That's what makes trigonometry so powerful. So I made the same triangle, so it kind of makes sense that the opposite over hypotenuse for that triangle is exactly the same as the opposite hypotenuse of all those other triangles. Any guesses? So what's our guess on, whoa, I hit the totally wrong buttons. Here we go. Sine of 325. Positive or negative? Guess? Negative? Yes. Cos 325. Guess? That one is positive. And tan? Guess? Oh, the tan is negative. So, with what we got here, we got the sine was negative. The cos was positive. And the tangent was negative. And what I'd like you to do right now is I'm going to take out a green highlighter and I just want you to highlight the positive ones. So in quadrant 1, I can highlight this whole box because all of them were positive. In quadrant 1. But in quadrant 2, only sine was positive. In quadrant 3, only tangent was positive. In quadrant 4, only cos was positive. So we can extend trigonometry beyond quadrant 1, but we still use regular triangles. And instead of using the big angle, we think about using the reference angle. But as we move from one quadrant to the next, certain things happen. Some are negative, some are positive. And you're going to have to remember this. And the easiest way to remember this is something called the cast rule. And the reason it's called the cast rule is because we draw all 4 quadrants and we put the letters C, A, S, and T in those 4 quadrants. And we call it the cast rule to help us remember this. So the cast rule isn't really a rule, it's like a memorization technique. Now, how does that help you remember? What do you think the C, the A, the S, and the T mean, and how do they help you remember the positives and the negatives? Any guesses? What do you think, Connor?
Guessing C is cosine.
C is cosine, good.
S is sine. T is tangent. A is anything. All.
Ooh.
I think all.
And what does the cast rule tell us? Which is positive? In quadrant 1, which ones are positive? All of them. In quadrant 2, which one's positive? Sine. In quadrant 3, which one's positive? Tangent. And because it spells cast, I mean, it could have been the astic rule. It just doesn't quite ring the same if you, it kind of makes sense that you would start in quadrant 1, right? But astic, it just doesn't ring as well as cast. Even you could read it backwards, maybe acts, like an actor, acts. But I don't know, that's a harder English word to say. When you, like, taken out of context, like it's okay, like, he acts well. I feel like I can say it in a sentence, but when I just try to say acts, I don't know, by itself, I struggle. Maybe it's a me issue, I'm not sure. So they decided on cast because it's easy to say, and this tells us where things, I don't know, it's a positive rule. It tells us where things are positive. And it's a little bit connected to our coordinates. So if I draw something in quadrant 1 and I had a point here, I'm going to just, looks like I've gone, just estimating, let's say I've gone over 4 up 2. Would you agree that that point is 4, 2? I know that this length is 4 and this length is 2 as a result. Now in quadrant 2, this point would be negative 4, 2. Because I've gone backwards. For me personally, I would still say the length of that side is 4, but as a coordinate, it's like a negative 4. And we could do a squared plus b squared equals c squared and get the hypotenuse. And when you square something, it becomes positive. So we always consider the hypotenuse as a positive number. But if this is a negative 4 and this is still a positive 2 because it's going up, and my hypotenuse in this case is going to be the square root of 20, which I could reduce to 2 root 5, but we don't need to review units right now. My opposite over hypotenuse would still be 2 positive numbers. But now my adjacent over hypotenuse, which is cos, we think of a negative number because we've gone backwards. And that's one of the reasons cos becomes negative. And tangent would be opposite over adjacent. And I have a 2 over a negative 4 now. That's why tangent is negative in quadrant 2. And if we look at quadrant 3, this would now be negative 4, negative 2 if I labeled that same point. And I've gone back, so I could think of this direction as a minus 4. And I've gone down, so I could think of this direction as a minus 2. And the hypotenuse would still be square root of 20. Oh, I did review unit and wrote 2 root 5. And can you see that opposite over hypotenuse is now negative? Adjacent over hypotenuse is now negative. And opposite over adjacent for tan in quadrant 3 would be a negative over a negative, which is positive. And we could do, if we wanted to, the same thing in quadrant 4. And now you can see why cos is the positive one, because the adjacent side is positive over the hypotenuse. Sine would be the opposite, negative 2 over the hypotenuse. This is going to be very, very important, because we're going to be solving, one, we're going to solve triangles bigger than 90 degrees. And 2, we're going to start solving questions that look like this. We're going to say, I know that tan of some angle is equal to negative 0.3. Can you tell me all the angles from 0 degrees to 360 degrees where that works? Well, one of the things that you're going to take out of this cast rule is right away, when you see that tan of theta is equal to negative 0.3, I actually actually, I feel like I want to use cos, just because it's more interesting for me. Cos of theta is negative 0.3. What are all the angles that could do that? Between 0 and 360. Well, that's once around the circle, and if I think about my cast rule, can you see right away, I know it cannot be in quadrant 1. Because cos was negative. In fact, it also can't be in quadrant 4. I know that my answer has to be in quadrant 2 and quadrant 3. But when I go to my calculator, I run into an issue. Because if I would do, I want to find the, right? Oops, I hit the wrong button. Right? If you want to find angle, you do cos inverse. And if I do negative 0.3, it tells me an answer, 107 degrees. That seems reasonable, right? Where's 107 degrees? In which quadrant? Second quadrant. Okay. So I have my answer in my second quadrant, but I don't know my answer in my quadrant 3. My calculator only gave me one answer. So there's a couple ways that you could go about this. We figured out one answer was 107. If you knew 107, you could find the reference angle, and if you have the reference angle, then you could go and use that reference angle to find it in quadrant 3. That's one method. What we're actually going to use as our method is we're going to find the reference angle first. And our symbol for a reference angle will be the angle with a tiny little r, saying we're looking at the reference angle. And the reference angle, does it make sense that whatever your reference angle is, it'll always be the one in quadrant 1? Is exactly the same? And in quadrant 1, cos would have been positive. So if it's negative 0.3, and we wanted to find the one in quadrant 1, can you see that it would have been positive 0.3? And so I'm going to go back to my calculator. And pretend I actually didn't do this, because the proper technique, we would do cos inverse of positive 0.3 first, and be like, oh, my reference angle is 72.542. If I wanted to find it in quadrant 2, and I had the same reference angle, does it make sense that you would have to go 180 degrees minus that reference angle? If I did 180, which is way too far, halfway around, but I subtracted that reference angle, I would get this answer that I wanted to begin with. And in quadrant 3, here's the angle in quadrant 3. This is what I want to find. Here is my reference angle. Does it make sense in quadrant 3 that if I took 180 and I added the reference angle, I would get exactly what I want? So I'm going to go back to my calculator. I'm going to start off with quadrant 2 and say 180, thank you, minus my reference angle, which I'm going to just highlight it here. And look, surprise, surprise, it gives us the 107 that we found earlier. Makes sense, 107.458. But now I can also find my quadrant 3 one, because I can go to my calculator and go 180 plus, and I'll go highlight that number again, and get 252.542. Write it in as a note there. If we find our reference angle first, which for your calculator, your reference angle is the same as quadrant 1, and this is true for all of them, sine, cos, and tangent. They will all be positive in quadrant 1. Then once you have that reference angle, it's really helpful because I could find the angle in quadrant 2 using my reference angle. I could find the angle in quadrant 3 using my reference angle. Right? The other option was, like when we typed in cos inverse of negative 0.3, it gave us the 107. You could do 180 minus the 107 to get the reference angle, and then use the reference angle to find quadrant 3. But the calculator does something a little bit different for each of sine, cos, and tan. For cosine, and this is what my AP Calculus was just studying the reasons for this the other day. For cosine, when I do cos inverse of negative 0.3, it gave me an answer in quadrant 2. If I do tan inverse of a negative angle, it gives me a negative angle. Negative angle, that would be in quadrant 4, negative. So cos inverse of a negative gives you an answer, a positive answer in quadrant 2, but tan inverse of negative gives you a negative answer in quadrant 4. Sine inverse of a negative answer gives you a negative answer in quadrant 4 as well. This is kind of weird. So, because that's kind of weird and kind of different, we like to do things to make things simple and easy. Simple and easy is finding the reference angle first. But what you have to remember is you always have to do, reference angles are in the same as quadrant 1 answers, so we always use a positive value. So the big idea of today is we're extending angles beyond 90 degrees. It uses actually the same trigonometry you used all along, but now if you had something like 170 degrees, you'd be like, oh, that's a reference angle of 10, so I'm thinking of a right angle triangle of 10 degrees. But because it's situated in quadrant 2, I also have to consider that sometimes I need to make things positive and negative, where our cast rule helps us remember that. All things are positive in quadrant 1. Only sine is positive in quadrant 2. Only tangent positive in quadrant 3. And only cosine positive in quadrant 4. Okay, which means you can circle already questions 3, 4, 5, and 7. Thank you. But with this, we can do example 1. Together. Whew. Awesome. Oh, they used the same numbers I did. That's just pure luck. We'll see if my numbers give us 35 degrees or not. See how close my guess was when I saw the 35 degrees. So the point, -2 -4. Lies on the terminal arm of an angle theta in standard position. So here's my angle theta in standard position. Now, anytime you have a point, you can make a triangle. And here, I hope you can see, like, I could easily make a triangle with the x-axis or with the y-axis. A temptation sometimes is to go from this point and go to the y-axis because it's closer. Right, we're lazy. Let's go to the closest one. No. We have to make sure that we always go to the x-axis because that's where your reference angle is. Your reference angle always is the angle between the terminal arm and the nearest x-axis. Now on this triangle, I know this length is 2 and this length is 4. I know some people like to label -2 and -4 because it's to the left and down. I like to label them positive so we can think of regular trigonometry back in grade 10. I have a right triangle. Could you solve this right triangle? Yes. Could I do a squared plus b squared equals c squared and get the other side? Yes. In fact, it's kind of nice that we did this before because you know this is the square root of 20. And I can simplify it to 2√5 already. So part A is asking us, can we write sine of theta, cos of theta, and tan of theta? Yes. Because if we think about SOHCAHTOA and our normal trig ratios, I know that sine is the opposite side over the hypotenuse. So that would be 4 over 2√5, but it's going to have to be negative because we're in quadrant 3 here, and the only one that can be positive in quadrant 3 is tangent. So in some ways people like it to say, well, if I labeled that as -4, I would get that right away. I personally always bring back the CAST rule and check my things with my CAST rule at the end. I know that cos is going to be negative because it's in quadrant 3. It's the adjacent side over the hypotenuse, so it's going to be 2 over 2√5. And I know that tangent's going to be positive, opposite over adjacent, 4 over 2. What's the problem with my answers, though?
Simplified.
They're not simplified. Which one would you like to do first? Sine, cos, or tan?
Cos.
Oh, I thought you picked tan. Tan's the easiest one to simplify, right? It's like, woohoo! I did that one. Can someone else do the rest? Right? That's the strategy. You do the one, pick someone else to do the rest. What do we have to do with the sine and the cos one? We have to rationalize the denominator. So I just have to get rid of the √5, so I only have to multiply the top and bottom
√5 over 5.
by √5 over 5. Which will leave me with -4√5 on the top and
2
√5 times √5 will be 5, so 2 times 5 is 10. Okay? And the second one, same thing. I'm going to get -2√5 over 10. Are we done? No, not done yet. Because the 4 and the 10 could be simplified to 2 over 5. And the 2 and the 10 could be simplified. There we go. Did the textbook simplify them at the bottom? No. And the reason they didn't is it could be that a teacher decides to teach the trigonometry unit before the square roots unit. Which is weird because you did it one way and you get used to the way that you learn it.
That makes sense. This is to like build your foundation.
right? Because the answer did do the 2 root 5 though, right? So they were using it a little bit. Anyways, these are the simplified answers. Now B, you have to find the angle. And finding an angle, you could use any one of these. One of them, though, does seem to look like it'd be easier numbers than the other ones. So I would probably recommend starting with this one. It's just because the numbers are nicer. Tan of theta is equal to 2. What's going to happen if I do tan inverse of theta? I mean tan inverse of 2 to get theta. I'm going to get an answer in quadrant 1. Because regular trigonometry dealt with regular triangles always gives you angles between 0 and 90 degrees. So it always gives you answers in quadrant 1. So what you're really finding if you did tan inverse here is you are finding the reference angle first. My reference angle is what's going to happen if I do tan inverse of 2. I go to my calculator to find out what that is. $63.435. Now, if you have that and you think about quadrant 3, does it make sense that this angle is going to equal 180 degrees plus your reference? So I can go back to my calculator and take that 180 and add that reference angle I just found. 243.435. What did it ask us to round to? Nearest degree? Woohoo! Good, because I had already forgotten those decimal places. Save myself some time. Question?
In 10 words, describe what a reference angle is.
10 words.
Oh, do all over these.
Yeah, well, I know, I'm just trying to do this. 10 words. Yeah,
As many words as
okay.
you want, actually.
The reference angle is the angle between the terminal arm.
Already dead.
Nearest x-axis. I lost some grammar marks, I know.
Okay.
Okay, but that was exactly 10. Okay.
Could you do that again?
No, don't. I can do it infinitely more times. But you just have to watch the video and listen to that part over and over again. Okay? So the nearest, it's always, here's my terminal arm, positive angle back to the nearest x-axis. Because that's where your triangle is made. That's the same triangle as it would be in quadrant 1, in quadrant 2, in quadrant 3, in quadrant 4. And this is how we extend trigonometry beyond 90 degrees. We're really just doing 90-degree triangle math over and over again, but we're making a rule of saying, oh, but in quadrant 3 here, sine and cosine are going to be negative, and tangent's going to be positive. So that's our little difference. In fact, we said we just went to 360. There's nothing stopping us from going to 720. Right? If I did 400 degrees, its reference angle would be 40 degrees. It would have the exact same triangle as the 40-degree triangle. So everything I do for sine, cos, and tan for 40 degrees, just so you see that I'm not lying here, I'll take out the calculator. Right? I do sine of 40, maybe. No, because I have my pen off. I do sine of 40, and then I do sine of 400, they're exactly the same, because they have that same reference angle. So if I wanted to do trigonometry at 400 degrees, I could. But really, I'm just doing the same thing as triangle, that same triangle of 40 degrees in quadrant 1. Right? Cos of 400 degrees is going to be exactly the same as cos of 40. They're both in quadrant 1, they'll both be positive. Tan of 400 degrees is exactly the same as tan of 40. They're both in quadrant 1. What's this going to equal? The same. Because you see 720 plus 40, this would have a reference angle of 40, is exactly the same. So now we've got trigonometry way beyond 360 degrees. Okay, circle questions 6, 10, and 11. Make sure that I answer all the questions. I did, and I rounded correctly. And I included my degree sign for my units.